Hello all, welcome, welcome, welcome. Just whilst you're coming in, what I'm going to do is share my screen as always so that you can see the starter tasks. And those starter tasks, guys, I'd really like to encourage you to have a go at answering these in the Q&A today. These questions on the screen are all based on what we did in our previous webinar, and they are tough. But what I want to reassure you is that the very first thing I'm going to do with you today is go through some of the work I set you last week, because some of your teachers had reported that perhaps you found it a little bit difficult, which is totally normal because this is some of the toughest stuff in this module. So what I'd like you to do is to have a go at these 4 questions. Now, if you have paper, you could have a go at writing them down. If you don't, I'd really like you to try and get them in the Q&A, and you can answer that question anonymously if you'd like. But what it will do is it'll give me an idea as to who knows what, and also just in general what the level of knowledge is of you guys in the webinar at the moment. So the questions are, what is Le Chatelier's principle? So in general, don't worry about word for word if you can't remember it, but thinking about what in general it means. In a reversible reaction, if you increase the temperature, which sort of direction will it go towards? If you increase pressure, which direction will it go towards? And lastly, what happens when you increase concentration of one substance in a reversible reaction in terms of the shift of equilibrium? So where does it shift towards? So I'm going to give you a few minutes. I just want you all to have a go at this because it is important for what I'm going to go through with you in a second. So I have some answers already in the Q&A. They're very, very good. What I would remind you is that we're talking about yield. So when I say direction, I mean, does it go in the forward direction or backward direction? Does it go, for example, with temperature, in the endothermic direction or the exothermic direction? When I'm talking about increasing pressure, do I go to the side with the fewest molecules, or do I go to the side with the most molecules? And then in terms of concentration, we're trying to figure out, do we move towards where we increase the concentration, or do we move away from where we've increased the concentration? So a couple more minutes, guys, just while we welcome everybody into the webinar. And then the first thing I'm going to do is go through this with you and to show you how to answer a question on it. But all have a go. I'd like to see some work in the Q&A. You can do it anonymously. Fantastic, excellent answer there. I won't call you out because I don't know how many people feel comfortable with being called out, but excellent answer about what Le Chatelier's principle is. Brilliant. That word equilibrium, very important to put in there. Good, 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 excellent, good. No one said you had to write full sentences. I'm absolutely fine with the one-word answers. It's good to see you getting involved. Good, good. Now, yes, I'll go through that in a second, actually. That's a really good point some of you have put down. Okay, so just before I go through the work from last time, let's go through these questions then. So what is Le Chatelier's principle? Well, there's been some absolutely fantastic answers in the Q&A, but Le Chatelier's principle is the idea that if you have a reversible reaction at equilibrium, when you make changes to that condition, to the equilibrium, so for example, if you increase temperature or you increase pressure or you do something to the conditions, then the position of equilibrium is going to shift to try and counteract the change. Now, when I go through the answers to the next 3, there are 2 kind of levels in which you need to know this. Now, the first level is know what happens. That what will get you some marks. Then we add on the why. Okay, and the why is the useful bit for when we do more 6-mark questions and to push your grade up to those 7s, 8s, and 9s. So what happens when you increase temperature in a reversible reaction? The equilibrium shifts to the endothermic direction. And that will depend when you get a reaction, they'll tell you which way is endo and exo. But it goes towards the endothermic direction when you increase temperature. That's the what. The why is because the equilibrium shifts to try and counteract that change. And in an endothermic reaction, you absorb the energy. So if you're increasing the amount of heat energy in a store, well, in an endothermic direction will absorb that to keep it balanced. Okay? What happens when you increase pressure in a reversible reaction? Well, when you increase pressure, the equilibrium is going to shift to the side where there are less molecules, because that is going to bring about some balance as well. So the what is when you increase pressure, the equilibrium shifts to the direction where there are the fewest molecules. And you have to work that out, and I'm going to show you how to do that in a second. The why, again, is because if you increase pressure, the equilibrium is going to shift to where there's less already, so that when you increase the pressure, it's trying to balance that out across it. And lastly, nice and simply, what happens when you increase concentration of one substance in a reversible reaction? Well, the equilibrium will shift away from that. So if you have A plus B, it gives you C and D, and you increase the concentration of A, well, that equilibrium is going to shift in the direction towards C and D. You're going to make more of C and D, and that's because you've already got more of A. And so you have an increased amount of reaction on that side. Now, before I go through what we did last week, I just want to clarify what we're going to do this week. So as always, we have a webinar, which you are in at the moment, which is great. And we have an embedded video that's been made by Miss Yavi. It is exceptionally good, these embedded videos. She takes you through a very specific bit of topic in more detail. So it's just a little addition. There is a quiz for you to do using the slides and additional resources if you need to. And then there are some exam questions that your teachers will have a look at. And these, again, have the same format as they always have. Now, on that note, I just want to share my iPad screen with you because I want to take you through one of the questions that we did last time. And the reason I'd like to take you through this is when I spoke to other science teachers who teach you guys, they said to me that you appeared to be finding this week's topic quite difficult. And they saw that because they felt like they were getting fewer submissions. So less of you were submitting work. And when you were submitting the work, it often appeared like perhaps you had the wrong end of the stick. Now, what I'm going to take you through is a question which is all about Le Chatelier's principle. And this was a question that was on your work from last week. The reason I want to take you through it isn't because I just want to give you the answers, because, guys, the answers are here. But the reason I want to take you through it is so that you understand how it's answered. And for you guys as higher students, it's on these sorts of questions that we need to really push ourselves getting some additional marks. So let's look at this question. Here you've got an equation given below. So ammonia is produced from nitrogen and hydrogen, and here is the equation. Now, when you do a question like this, you want to try and think about what information you're given in the question before you even have a go. Now, you also are told that the forward reaction is exothermic. So here's what I can do before I even get started on the rest of the question. First thing I can do is I can count the number of molecules on either side of this reversible sign. And the reason I'm going to do that, Year 10, is because I know that when I answer questions on Le Chatelier's principle, they may ask me about pressure, and then I'm going to need to know about the molecules. So if I look on the left-hand side, I can see I have 1 lot of nitrogen and 3 lots of hydrogen. Now, remember, when we talk about molecules, we're not talking about atoms. We're talking about the actual molecules themselves. And what I'm going to do is zoom in to hopefully make this a bit clearer for you. So if I were to draw this N2, I would simply be drawing this one molecule. And over here, if I were going to draw 3H2O, 3H2, I would be drawing 3 lots of H2. Now, I know in total there are 6 atoms of hydrogen there, but that's not what is important for this particular topic. It's about number of molecules. So overall, on this side, I'm going to just put a 4 to show that there are 4 molecules on the left-hand side. On the right-hand side, I have got 2NH3, which is this molecule twice. And I don't expect you to know the shape of these molecules. This is just me trying to help you visualize it. And so that's 2 molecules of NH3, so I'm just going to write 2 at the top. That's going to help me later on. The next thing I'm going to do is look at this second part of the information they've given me in the question. The forward reaction is exothermic. So if the forward reaction is exothermic, and we can write that on here, then what must be the backward reaction? Answers in the Q&A, guys. If the forward reaction is exothermic, then the backward reaction must be fantastic, good, brilliant. It must be endothermic, and we learned that when we did reversible reactions. So I'm just going to quickly draw on here endo as well. Okay. Now, none of that is actually the question yet. I've just done that because sometimes when you go into tests or you go into exam questions, you can feel that pressure. And sometimes this sort of thing can help take that pressure off. You just get down what you know on the page. So let's look at the actual question here. It says a low pressure is used. Let me highlight that rather than line through it. A low pressure is used. Okay, so that's obviously going to be important when we go into the question. Explain the effect on the yield of ammonia. Okay, so in this question, it's talking about pressure. And I know, because we've gone through it already, when I'm talking about pressure, I'm looking at the side with the fewest or most molecules. Now, you guys told me in the starter that when I increase the pressure, I go towards the side with the fewest molecules. Well, therefore, if I lower the pressure, I must be moving in the direction of the most molecules. So in this case, the equilibrium is going to shift to the left, because that's the side with the most molecules. And guys, I am not writing in full English because I don't want you to have to sit there and watch me write sentences for the next 5 minutes. Now, that is half of the question, because the question actually asks you, what is the effect of that on the yield of ammonia? Now, ammonia is this compound here. And if we shift the equilibrium in the left-hand side direction, which is the side over here where nitrogen and hydrogen are, well, then we make more nitrogen and hydrogen. So if I'm making more nitrogen and hydrogen, well, I'm going to end up making less ammonia because I'm shifting the equilibrium in the other direction, which is causing the ammonia to break down and convert back into nitrogen and hydrogen. So the yield decreases. There's your 2 marks, done. Now, let's look at the second question. A high temperature is used. Explain the effect on the yield of ammonia. Well, this is the same idea, isn't it? If we increase the temperature, we know that it will move in the endothermic direction. And that would be your first point. I don't have space on here. Well, I do if I move it, but it will shift to the endo direction. Because, you know, the endothermic direction is going to absorb that excess heat. You don't have to explain that for this mark scheme, but it's a good thing to keep in your head. Now, because you're shifting it in the endothermic direction, and we have already noted that the endothermic direction is towards the left-hand side, again, this high temperature is going to reduce the yield or decrease the yield of ammonia. Now, in this question, they haven't said it, but in some questions, they might say, well, why would you still use a high temperature if it's going to decrease yield? And hopefully you remember from last time that the reason we still use a higher temperature in a lot of industrial processes, despite the fact that sometimes it might reduce the yield, is because it increases the rate of reaction. And you don't want a reaction to be really, really slow, because it will end up being not very efficient and not very cost effective. It costs lots of money to keep the reaction going for that long. It's much more efficient to get as much product as you can in a short amount of time. So it's a compromise. Now, the last question is worded in a slightly strange way, but we've talked about temperature, we've talked about pressure, so now we're talking about concentration. And this question says, ammonia is removed from the reaction mixture. Explain the effect on the position of equilibrium. Now, if I'm removing the ammonia from equilibrium, so what they're basically saying is, imagine you're doing this reaction and you've got a pipe that will come off the reaction vessel that's going to collect the ammonia. So as you make ammonia, you're going to be collecting it and taking it away. That means overall in your reaction vessel, be it a flask or whatever you're doing the reaction in, you're going to have less ammonia. So the concentration of ammonia is decreasing. Now, we've already spoke about, if concentration increases, you move away from that side. Well, in this case, concentration is decreasing. So you're going to move towards it. And that makes sense when you think about Le Chatelier's principle, because if I'm reducing the amount of ammonia in the system, well, Le Chatelier's principle says that the equilibrium is going to shift to correct those changes. So if I'm removing it, it's going to shift to make more. So the equilibrium will shift to the right. Now, in the exam, you could say forward direction, but it's more correct to say right and left. So in this case, it will shift towards the right to replace the ammonia. And that is your mark. Now, I'm not going to go through the other questions on this, because I'd like to make sure we keep going and keep doing new content. But what I really want to draw your attention to, those of you that have had a go at this already, will realise that most of these questions are exactly the same, but with different equations. So this one is about ethanol, but again, they talk about yield of ethanol with temperature and pressure. And then in the other questions, you have a mixture of rates of reaction questions and yield questions. So this is stuff that is repeated. It's very repetitive. So if you know how to answer those questions about one type of reaction, you will end up understanding them for all of them. Now, I'm going to leave that there. If you do still have more questions on Le Chatelier's principle, when we go back to school next week, we will be recovering these topics, okay? And what would be really useful is if you could let your teachers know if this is something that you really do want to spend a bit of extra time on when you go back, because we're going to spend 2 weeks going over that. At the end of this webinar, I will take you through a bit more about what's going to happen when we come back to school, so that we don't sort of have to keep stopping and starting. So I'm going to stop sharing my iPad and reshare my computer screen, and we're going to crack on. Now, what we're going to start with now in this bit of the topic is we're going to talk about organic chemistry. And organic chemistry is a whole area of science, and a whole area specifically of chemistry. And predominantly, organic chemistry is the chemistry of molecules that contain carbon. And some people love it, some people hate it. I personally love it because I find it fascinating. Organic chemistry is how we can design and manufacture medicine. Organic chemistry is how we can make different plastics and different biodegradable plastics. Organic chemistry explains why, it's how we have different alcohols and different fuels. So it's really, really important. And we're going to learn about lots of different types of hydrocarbons and lots of different types of carbon containing molecules in the next 2 weeks. Today, we're going to focus on one family of chemicals, and we're going to talk about how we get useful molecules from a mixture. So this is the beginning of a wider set of topics, if you like. It's a really interesting topic in my personal opinion. So So we're going to start by talking about something called crude oil. Now, crude oil, it might be a phrase or might be something that you've heard of before. It is a non-renewable resource that's found deep under the ground in rocks. And if you can recognize this as an oil rig, this top right-hand picture, that's one of the methods of drilling underground to get this crude oil out of the ground. And crude oil is actually made from ancient biomass. What that basically means is it's ancient remains of plankton and very small animals that have died and been buried by mud to form this oil. It's a fossil fuel. But what's really important is that we understand that crude oil is a mixture of many different molecules. Crude oil, as we dig it out of the ground, so this big viscous gloopy stuff, isn't very useful on its own. It's useful when we split it up into different fractions, when we take different parts of it and we use it for different things. And crude oil is mainly made up of types of molecules called hydrocarbons. Now, hydrocarbons are pretty simple as an idea. Hydrocarbons are molecules that contain only carbon and hydrogen. And that is in the name. And it's important because I've done the quiz for today and I've been looking at loads of past paper questions. You'd be surprised how often that comes up. Tell me something about hydrocarbons. Well, they only contain carbon and hydrogen. Now, we're going to learn about quite a few different types of hydrocarbons. But the first thing I want to do is just introduce you to the idea that there are different families within that. So these are all called hydrocarbons, okay? They all come under that classification because they are molecules that are only made from carbon and hydrogen. But the different ones that you have down here have different properties. And we call each of these different families a different homologous series. Now, I personally hate that phrase because it's so complicated, but all it means, guys, is the family it belongs to. So the alkanes, that's these molecules here, they are a homologous series. Alkenes are a homologous series. Alkynes are a homologous series. And aromatics, arenes, phenols, they are a homologous series as well. Now, you guys, out of these, are only really going to look at these first two. We're going to look at alkanes and alkenes. And actually, today, all we're going to look at is the homologous series called the alkanes. Now, when I say homologous series, just to really make it clear, we're talking about a family of alkanes, okay? A family of molecules that all have similar properties and behave in similar ways. So let's go through alkanes in a bit more detail. Well, on the screen, I have got the 4 alkanes that you need to be aware of. Now, let's look at what these things have in common. So the 4 alkanes that you need to know are methane, ethane, propane, and butane. Now, what I want you to think of first of all is take the names of these different alkanes. I like to break them in half. So you've got the bit at the end, which is the ANE, and you've got the bit in the beginning, so meth or eth or prop. Now, the bit at the end is kind of like a surname. The ANE is like a surname. And that makes sense because if their family are alkanes and they all have the same surname, methane, ethane, propane, and butane. The first part of the word, though, relates to how many carbons it has in its chain. So meth relates to any molecule that has 1 carbon in its chain. Eth is any molecule with 2 carbons in its chain. Prop, 3, and but, 4. After that, it kind of makes a bit more sense because it goes it goes pent, hex, hept, so more like shapes, but we don't need to know those off by heart. It's just these 4 that we do. Now, the way to remember that is monkeys eat peeled bananas. Okay, that's a little thing to help you remember it. Monkeys eat peeled bananas. Methane, ethane, propane, butane. Now, in the exam, you may be shown a molecule and asked to name it. And you'll have to do 2 things. You'll have to figure out what's the first part of the name. So is it meth, eth, prop, or but, based on how many carbons there are in the chain? And the second thing you'll need to do is to work out which family it's from. Is it an alkane or an alkene, etc.? Now, we'll talk about alkenes next week, but alkanes have certain things in common. Now, let's look at each of these carbons in the middle of each of these molecules. Each carbon makes 4 single bonds. Now, carbon can only make 4 bonds. It's the maximum number of bonds it can make. And in alkanes, each of those bonds is a single bond to another atom. We say that alkanes are saturated because they don't contain any double bonds. That will make more sense when we look at alkenes. So for now, it's important to note that alkanes, we name them with the ending of their name. We put the ane bit at the end. And the first part of their name comes from the number of carbons they have in the chain. Alkanes make 4 bonds around each carbon, 4 single bonds, normally in like a cross shape. And the last thing we need to look at is this bit here, where it says Cn equals H2n plus 2. Now, some of you may be looking at that going, great, algebra. Some of you might be going, brilliant, algebra. They're different people. Let me explain what this means. So CnH2n plus 2 is a way of working out how many hydrogens you would have if you had a certain number of carbons. So for example, let's take propane here. If I've got 3 carbons, and so n equals 3, well, the number of hydrogens I would have would be 2n plus 2, or 2 times 3, because I've just said we've got 3 carbons, plus 2. 2 times 3 is 6, plus another 2 is 8. You can also think about it like this. Imagine you are looking at any molecule of an alkane. If you were to count the number of hydrogens on each carbon, well, you could go, each one is C plus C is Cn, which is 1, plus, gosh, Cn H2n. So each carbon makes at least 2 hydrogens, but there's an extra 2 on either end. So you've got the 2 connected to the backbone, and then you've got the 2 extras. Okay, but you will need to remember that alkanes, the way to work out the formula is CnH2n plus 2. So let's have a go together. In answers in the Q&A for me, this won't be difficult, I promise. If n equals 5, so there are 5 carbons in a chain, in an alkane, what would the number of hydrogens be? So if n equaled 5, what would the number of hydrogens be? Let's put your answers in the Q&A for us, guys. Let's see. Just smash them in there. As soon as you've got it, pop it in. So if n equaled 5, what would the number of hydrogens be? You're smashing it, year 10. You're absolutely smashing it. Well done to everyone who's getting those answers in. You can still bang them in if you need to. So if C equals 5, so C5, well then, using the formula we've got there, 2 times 5 equals 10, plus 2 would give us 12. So the formula for a 5-carboned alkane would be C5H12. And in real life, that exists. That's a molecule called pentane, because there are 5 carbons. All right, one more. Let's go with if n equaled 8. What would be the number of hydrogens? So if it was C8, what would the number of hydrogens be? Let's get that in the Q&A, guys. Brilliant. There are some of you who just straight off the bat. So remember, it's 2 times n plus 2. We know that n is 8 because I've just told you that. So how many hydrogens would there be? This is really good, guys. Fantastic. So 2 times 8 is 16, plus 2 would give you 18 hydrogens. Now, as a real extension here, what do you reckon you call an alkane that has 8 carbons? See if anyone can work that out. Based on like shapes, and we know what the suffix is. Got the right answer in the Q&A already. Fantastic. Brilliant. Brilliant. Now, you don't need to know that. That was just me being a little bit tricksy with you. But an 8-carboned alkane is known as octane. Well done, guys. It really is. Well done. Now, above that, it gets more confusing, but we don't need to go above that for now. Unless any of you want to do chemistry further on, well, then good luck. It is fun, I promise. So those are alkanes, and alkanes are super useful. We mainly use them as fuel, and different fuels have different properties. So sometimes when we think about fuel, we think petrol, or we think about like the methane that comes out of the gas taps at school. But there are lots of different types of fuels that are made of hydrocarbons. And it's important that we separate them out so that we can get the bits that we need for the purpose we need. And the way that we do that is through fractional distillation. Now, I was going to go through drawing alkanes with you, but I'm going to hold off on that for now, just because I don't want us to lose any time on fractional distillation. But we can go through that with you when you come back to school. So how do we go from this big gloopy mixture of hydrocarbons, that is crude oil, so lots of different hydrocarbons all in a big mix, to having them all separated out based on their chain length, so how many carbons are in their chain? Well, we do that through a process called fractional distillation. Now, this is a diagram that shows fractional distillation. Apologies, guys. What I'm going to do is I'm going to talk you through it. Then I'm going to pop up some notes that will be on the slides that you can use when you come back to it. And then I want to show you an example question. Okay, so you can sort of see how it might come up in the exam. Sorry. So fractional distillation, you start with crude oil because that's the stuff you dig out the ground. So we go from crude oil to the stuff we want in the end. And this is how we're going to do it. The very first thing that happens is that you heat that crude oil up very, very hot. So hot, in fact, that most of the compounds in crude oil are going to evaporate. Now, some of the compounds in crude oil will not evaporate. They'll be too long, too large, too viscous as a substance, so they'll just run off down the bottom. And we still use those really, really big hydrocarbons for things like tarmac. Bitumen is one of the molecules that is found that we use to make roads and things from. Now, as you go up the tower in this fractionating column, that's what this is called, the temperature decreases. So as you get higher up, the temperature gets cooler and cooler and cooler. And what happens is as you get higher up, the different molecules start to condense. That makes sense, doesn't it? We've heated it up really hot, and now we're going to let it slowly cool down. So some things are going to start to condense. As we decrease the temperature, we notice that different molecules condense at different temperatures. Those with the highest boiling point, and that means that you have to heat them up quite a lot to keep them as a gas, well, they condense down the bottom. Because as it starts to get cooler, they no longer have the amount of energy they need to stay as a gas. And so they condense back into a liquid and they run off down a nice tube to be collected. As you go higher and higher, different fractions, that's what we call them, condense at different temperatures based on their boiling points and are collected. Right at the top of the tower, you've got the compounds that don't actually condense within the temperature in the column, and they're collected as gases. And we know, guys, that methane, for example, is a gas. It's a fuel, but it's a gas. We use it in our gas taps, and if you've got a gas cooker, you use it there as well. Now, when we go up the fractionating column, we need to really realize that different fractions are useful for different things. So down at the bottom, you have got the molecule, the substances that are more viscous. Now, viscous is how thick, how gloopy a material is. Viscosity is something that you need to be able to understand. And viscosity is to do with, like I said, how easy it is to pour it. If it's very viscous, it's very gloopy. It's a bit like custard, okay? The lower viscosity is more runny, all right? So as you go up the fractionating column, the substances that you remove are less viscous, okay? I'm going to explain why in a second. Also, as you go up, the substances become more flammable. And the reason they're more flammable the higher you go up is because they're more readily able to react. They don't need as much energy to stay as a gas. And when they're a gas, they're easier to react. We talked about this when we talked about rates of reaction and about how the smaller the particles were, the more easy it was to get them to react. It's a similar idea. Now, that's all on there for you to read through at your own leisure. I'm going to keep it on there on the slides that will be in your classroom, but it's an explanation of what I've talked about. Now, let's think about the why. We've talked about the what. Now, in an exam question, if it's a 4-mark question, it might say to you, what happens in fractional distillation? You heat up the crude oil. The compounds mostly evaporate. You collect different fractions at different temperatures based on their boiling points. Those with the highest boiling points condense down the bottom of the tower where it's still hot. Those with the lowest boiling points condense nearer the top of the fractionating column. Now, why? Well, here is something that we need to be very, very aware of, and that is the longer the molecule, the higher the boiling point, the more viscous. The smaller the molecule, the less viscous, and the easier they are to evaporate, and so they condense less easily, okay, because they don't condense at these low temperatures. Now, why is that? Well, I've drawn some dots here to show you what we call intermolecular forces. Now, don't be too thrown by that. What that basically means is how much are those molecules holding on to each other closely. Now, intermolecular forces are between everything, okay? When you have a glass of water or you've got water in there, they have intermolecular forces in there that kind of hold the water molecules together. Now, in smaller chains, like the one I have up here, I've got pentane up here, the interactions are between 5 different carbons. So you have the chain interacts with another chain across those 5 carbons. And so their intermolecular forces are there. On longer chains, such as this one here, there are more intermolecular forces because there are more interactions, because the chains are longer. They can interact at more points. Now, you don't really need to know that, but I want to explain it to you. But what you do need to know is that longer chains come off at the bottom of the fractionating column because they have a higher boiling point. And they have a higher boiling point because the intermolecular forces between the molecules are higher. That means that it's harder to break those intermolecular forces or overcome those intermolecular forces. It requires more energy to separate them and to turn them into a gas. Whereas the smaller the molecule, the fewer intermolecular forces, the weaker the intermolecular forces. So therefore, you don't need as much energy to pull them apart to turn them into a gas. So in summary, fractional distillation is used to separate different hydrocarbons in crude oil. You heat crude oil up to very high temperatures. You can see here, that's above 300 degrees. Most of the hydrocarbons or the compounds in crude oil will evaporate. Some will not because we haven't heated them up hot enough because they've got such a high boiling point, and those are removed from the bottom. As you go up the fractionating column, as you go higher up, the temperature gets lower, and different fractions condense at different temperatures based on their boiling points. Those with the highest boiling points condense at the bottom of the tower, and those with the lowest boiling points can remain as a gas at cooler temperatures, so condense nearer the top. Some remain as a gas and are collected as a gas. The differences between those boiling points is due to the length of the carbon chain, or how big the molecule is. Those with long carbon chains have strong intermolecular forces which hold them together, which means you need lots of energy to overcome the forces. Those near the top with shorter chains have weaker intermolecular forces, which means you don't need so much energy to overcome the forces and therefore can remain as a gas at lower temperatures. Additional things that you need to know about fractional distillation is that the ones nearer the bottom are more viscous, which we know means more gloopy, less running. And the ones nearer the top are less viscous, but are more flammable, okay? They're easier to set fire to. If we were in the lab, we can show you this, okay? We can show you how easy it is to ignite certain things as opposed to some of the longer chained fuels. It's also important to note, year 10, that these different fuels have different uses. So you can see that petrol up here, this is what we put into our cars. That's quite a short chained molecule, okay? It's flammable. It gets ignited within the engines of your cars, all right? Methane, which is coming out right at the top up here, is a gas as we use it. Propane, the same if you go camping and you have like a gas-fired little stove thing. As you come down here, diesel is actually a much more viscous, a much longer chained molecule. Some vans and cars take diesel fuel. Bitumen, which is used for tarmac and for lining your roads, basically, it's really viscous, really long chained molecule. And that makes sense because it's a real sticky molecule when they put it on the ground. I don't know if anyone's ever seen them tarmacking a road before. It's really sticky stuff, okay? And that goes down onto the road. So that's fractional distillation. Now, what I want to that's the video that I want you to look at, which goes over fractional distillation in a little bit more detail from Miss Yarvi, and that's specific. She's going to take you through that. But what I wanted to show you is an exam question, because like I spoke about with Le Chatelier's principle, there are only so many ways they can ask questions about this, and I want you to see what they want you to say. Now, in the quiz this week, I've given you quite simple questions because there are lots of short answer questions about this. But alternatively, there are also quite a few 6 markers. Now, this question I've got on the screen for you is actually a 4-mark question. And it talks about how crude oil is separated. So let's read through it together. Figure 1 represents a fractionating column used to separate crude oil. And they've given you the diagram. They often give you the diagram. So if you can recognize that as fractional distillation, you're sailing. Now it says, describe how crude oil is separated using fractional distillation. Now it's only worth 4 marks. So what should be going through your head? Well, all of the compounds, or nearly all of the compounds, are evaporated to begin with. They condense at different temperatures based on their boiling points. Can we talk about chain length? Do we need to talk about carbon chain length at this point if it's only a 4 marker? Well, let's have a look. So in this 4 marker, the marks you get are for saying it's heated so that the fractions evaporate, or all the hydrocarbons evaporate, okay? You can also say vaporize, that's fine. The second mark you get is for simply saying that at the bottom it's at its hottest and at the top it's at its coolest. It decreases as you go towards the top. The third one, as the vapors or the gases rise up, they start to condense. And your 4th mark is for saying that they condense based on their boiling point. That's what makes them come off at different points. Now notice that's a 4-mark question. You haven't been asked about the length of the carbon chain. You haven't been asked to explain that. So what about if you got it as a 6-mark question? Well, here you've got your 6 marker. And it says pretty much the same thing. The question is almost identical, but this one has the 6 in brackets. Now let's look at the extra information that they want from you. So what they want for a 6-mark question is they want you to logically link it to make it make sense. So talk through it and explain it in detail. So indicative content that you might say. Crude oil is heated. The hydrocarbons evaporate. Vaporize just means evaporate. Vapors enter the fractionating column at the bottom. So it comes in via the bottom of the column and then it gets cooler as you go up. You could also say that they start to condense and they become liquid, but they become liquid based on their boiling points. So the higher the boiling point, they condense lower at the bottom. Then you start to bring in the idea of chain length. So 6-mark question, you're bringing in the idea of the different carbon chain lengths. The fractions with the smallest molecules in them have the lowest boiling points, and so they're collected at the top of the column. The fractions with the longest chain length, they have the highest boiling points, and so they're collected down the bottom. Now that has been the entire webinar, and I'm not going to go on for too much longer because I don't want us to get cut off. If you are struggling with anything from this webinar, watch it back, look at the slides, and use the additional resources on the worksheet. You've got the quiz and the worksheet to do. And what I've also included on this slideshow is if you are still struggling with anything we've done in the past, here are the video links to everything so far from C2. If you have any questions, you're more than welcome to hang on for a minute or so, but the next webinar will be beginning soon. It has been an absolute pleasure, Year 10, to see you all here. Let me know if you need anything at all. Good luck with your work from this week, and we look forward to seeing you back in school next Tuesday. More details about that will come out in the next couple of days, and we will be going through the stuff we've done online in lessons in a condensed way to help you catch up if those of you who are struggling. You are more than welcome to leave now, guys. Go off and get on with your work or go to your next webinar and have a lovely rest of your day. It's been a real pleasure to see you all. Thanks a lot, Year 10. Okay, so it doesn't appear that anybody... Oh, will we be recovering the whole topic? Well, we will be covering the things that we've done so far, Soren, but we'll only be doing so based on what your class needs. So your class may want to go through specific things in more detail. So others may not need to go through it in as much detail. So it'll be class by class, and then we'll be moving on after the first 2 weeks. Okay, so we'll be refreshing what we've done in the first 2 weeks and then moving on. Okay, guys, so I think that's answered the questions. I'm going to stop the recording now, and I will see you all next week.